All right, welcome everyone. I believe we're good to go. So hope you've been enjoying droidcon so far. Generally, when we create source code that is correct, we also expect this to run correctly on our phones. But what if that doesn't happen? What if we get something like this? So this presentation will be about helping you understand the translations that go on from your source code to code that actually runs on your device and how situations like this are possible. So I'll also try to relate it to specific bugs or cases that have happened. So in this case, this was an R8 bug that you can look up where someone created source code that is technically correct, but somehow somewhere in the translation something was wrong. So as I mentioned, so the presentation will be about the code that you write, so source code, the translations that it goes through, and what it actually looks like when it runs on your device. Certain maybe bugs or unexpected behavior that we'll look into in more detail, and then also sharing some different types of techniques or tools that can help you understand, like inspect what is going on inside this translation, or maybe help debugging certain types of issues. Maybe just a quick word on who I am. So my name is Ruben Pieters. I am a compiler engineer working on DexGuard. DexGuard, you can see it as a Dex recompiler. What exactly Dex is, if you don't know, we'll get into later. But basically, me and the team I'm in, and the DexGuard team, we work with these intermediate languages on a daily basis. So we are basically have compiled some certain things that we think are interesting also for app developers to know. So that's what this presentation is about. A quick overview first of like what we'll be going through, what in the presentation, and then we'll dive into the more nitty-gritty details afterwards. So these are essentially kind of the 4 steps that source code goes through. So you start with Kotlin or Java source code. This then gets compiled to Java bytecode. Then it gets compiled into Dalvik bytecode. And then potentially it might get compiled into machine code because both Dalvik bytecode can be interpreted or it can be compiled into machine code. An interesting tool that you can use, or like a website, is Compiler Explorer, which is available online as a website, where you can basically really explore with kind of source code and immediately view what this gets translated into. So it has support for a lot of languages, and among them also, for example, Android Kotlin source code. So this is, in the next few slides, I'll be basically putting compiled code on the slide that you can also view with this web tool. So let's go through the 4 different steps, and let's just have a quick look at what that looks like. I'm not really going to go into details of like the specification of all of these bytecodes and languages. There's lots of good resources online for that. I just want to quickly have a very brief introduction. So on the top left, you see Kotlin code. You're probably familiar with that. As I mentioned, this gets compiled into Java bytecode that looks something like this. Just the thing I want to highlight is that Java bytecode is stack-based. So if you look at the first 3 instructions here in the Java bytecode, these correspond to the multiplication of the 2 or the input parameter. So iload0 will put the first input parameter on the stack. We will do that twice, so we have 2 things on the stack. We then have an imul instruction, so a multiplication of integers. This will then pop 2 things from the stack and put the multiplication back on again. The next step is from Java bytecode to Dex bytecode. Dex bytecode can be textually represented as it is on the slide right here. And then the interesting thing to highlight here is that Dex bytecode is no longer stack-based, it's register-based. So the multiplication instruction is now replaced with something that takes 2 inputs from the same register, P0, which is the first argument, which will, in an instance method, correspond to this. So, but in this case, it's a static method, so we just have our the integer input. So we take this multiplication from the integers, put it into V0, And this DEX bytecode is something that can be interpreted by your device. Then we have this next step, going from DEX bytecode to machine code, which is what DEX2O does. So this depends, of course, on the architecture on the device, but typically this will be compiled to ARM for ARM devices. In native or like in machine code, there will be a bunch more other setting up, things like stack canaries and so on, which is what happens above. But we still see the multiplication instruction there as well. So that was in a nutshell, kind of briefly what kind of this bytecode and machine code looks like. And in the rest of the presentation, we'll go into a bit more details. But what is interesting, I think, for you as a developer is that you interact with all of these aspects. So even though, for example, Java bytecode is not something that runs on Android devices, it is something you interact with because unit tests run in the JVM, the Java virtual machine. So even though Java bytecode is not something that runs on an Android device, it is something that you also interact with. And then, of course, Kotlin and Java source is what you develop, Dalvik bytecode and machine code is what actually runs on your device. So let's get into a bit more details into this first step, the source to Java bytecode. So as we saw before, Java or Kotlin code, source code, gets compiled either by Java C for Java or Kotlin C for Kotlin into Java bytecode. This Java bytecode can run on a Java virtual machine. So if you have typically you will have a JDK installed, so you have the Java command available. You can run Java bytecode, so we can run this main.class file. It will run the main method, and then we will see that it prints hello world by executing this command. Let's get into a more concrete example where it could be interesting for you to see what is going on with these class files. In this specific example, we look at a sort of simple Kotlin file where we have a function with a default parameter. So we can, from Kotlin, we can call this by giving a string parameter for the name value, or we can call it without that value. If we try to call this from Java, we will see that we cannot call it without any parameter. So that might be a bit surprising because from Kotlin we can do that. Why can't we do that from Java? If we go to inspect how the Kotlin compiler actually compiled this, we can see that there is no actual method in the Java bytecode called greet with no parameters. So that's the reason why the Java compiler will complain that this doesn't work. So we can see the greet method with the string parameter. We can see the greet $default, which the Kotlin compiler will use when it is compiling, but there is no actual method without any parameters. There is a simple way to fix that if we want this, of course. So the Kotlin language provides the JVM overloads annotation, and then if we go to inspect the Java bytecode, we will see that this method actually gets added. So this is kind of a simple situation where just looking at the source code, it might be kind of surprising why something doesn't work, but looking at the Java bytecode that was generated, it might be like it's a lot more intuitive why something isn't actually working the way we expect it would be working. All of these intermediate files, when you go to Android Studio, you can find these in your build folder. So when you build your Android application, there will be class files generated by the compiler that you can also inspect yourself. So that's just to highlight where you can find these things if you find it interesting or if there is something you want to actually inspect or investigate. Let's go into the next step, the Java bytecode to Dalvik bytecode translation. So as I mentioned before, Android doesn't run Java code technically because it doesn't have a JVM. Instead, what it has is the Android Runtime or the ART, and the ART runs Dalvik executable files or DEX files. So that's why this translation is necessary, because it doesn't run class files, it doesn't run Java bytecode. The compiler that does this is called D8, so this is the DEX compiler that can transform Java bytecode into DEX files. And similarly, like we had before, where we can use the Java command to run Java bytecode, we can also use a command to run DEX bytecode. This is called app process. It's a binary that is on your phone, so you can push a DEX file onto your phone, use this binary to run DEX files on your phone, and then just in the same way that the JVM will call the main method, the DEX this app process binary will run the main method of your DEX file. So the JVM and the Android runtime are generally trying to sort of keep behavior equivalent in the way that if you run something in the JVM, if you run Java bytecode on the JVM, or if you run DEX files on the Android runtime, it will generally try to be the same or do the same things. But there are some cases where you can actually see differences. This is, I guess, mostly a benign example. I'm not sure whether it's actually relevant, but it's just a very simple example to illustrate. So in the JVM, for example, the array index out of bound exception, the message that you will get with this is index 4 out of bounds for length 3. While you try to run this on the ART, the message will be a bit shorter. It will simply say length equals 3, semicolon, index equals 4. So that's just a simple example to illustrate that the behavior can be slightly different. Sometimes these things are less benign, and then these will usually be considered bugs. So this is a specific example that someone made an issue for, where I don't know exactly what they were specifically doing, but basically the same code running on the JVM resulted in different behavior than the Android runtime. So for them to then investigate the bug, they kind of had to run the same code on the JVM, run the same code on the Android runtime, see exactly what the difference were to kind of help and see in what kind of situations this behavior occurred, these behavior differences. There's also sort of differences inherently in how the ART or JVM works, because the JVM works with Java bytecode, the Android runtime works with DEX code. There are certain functionalities that simply cannot be made available in one of the two. So for example, in the Android runtime, we can load DEX files in memory. This functionality is not going to be available on the JVM. And similarly for the JVM, there's going to be things that interact with Java bytecode in memory that are not possible in the Android runtime. And as I mentioned before, I think this is kind of a good difference to be aware about, because especially in testing, certain tests, like for example unit tests, will run on the JVM, but also more intricate tests like frameworks like RoboElectric. These work inside a simulated Android environment on the JVM, not on the Android runtime. While, for example, instrumented tests that run on actual devices, they will actually run on the Android runtime. So I think it's good to be aware of if you have these kind of cases where maybe the cost could be a difference between running in these two environments, to be aware of like where your tests are actually running. So let's also go into an example where it could be interesting to look into what has happened to the DEX files. This will be a bit of a longer example. I also want to introduce some additional steps that can possibly happen with DEX files beyond only compiling with D8. So when we translate Java bytecode to Dalvik bytecode, there are also other steps that can happen. So there can be an optimization step, which could be either ProGuard, which works on Java bytecode itself, or R8, which works during the translation from Java bytecode to DEX code. And then, or also possibly DexGuard, which DexGuard works on DEX code itself, or sometimes also on Java bytecode, because inside SDKs, inside ARs, there is only Java bytecode, there is no DEX code. So very briefly, what ProGuard or R8 do, because it will be relevant in the example later, it will shrink code, so shrink unused code, it will optimize bytecode, but the thing that will be relevant in the example is that it will transform names into different identifiers. So let's now dive into a more concrete actual example. So the setup of our example will be a situation like this, where we basically have an overloaded method where one class does not exist within the class path, so a class that is not available. We'll see how that can happen more concretely later. and then another method where we are calling, that takes a string parameter, which obviously will be available. So we will always be calling the method that has a parameter that does exist. The other one doesn't make as much sense at the moment. Just calling that method, obviously, it will just work. We can invoke it, and we will get the print. But what happens if we call this method by reflection? So calling it by name, and then the lookup still needs to happen of like what that method exactly is. Then we will see that this method, or we will get a no class def found error, which might be a bit surprising because calling this method regularly, nothing goes wrong, and nothing seems wrong with this method because the string parameter does exist. So why does this go wrong? For that we have to dive a bit deeper into what this class.get method actually does. It needs to look up like what the different overloads are, which classes are involved to decide which one to actually invoke. And during that process, it will try to load one of the classes that doesn't exist, and that's why we get this no class not def found error. But yeah, you might think, okay, why would we even write code like this in the first place? This seems a bit convoluted, so let's make it a bit more concrete on how this could possibly happen in a more concrete situation. So let's first make the does not exist thing a bit more concrete, like how could that possibly happen? So certain classes in the Android APIs are only available from certain API levels. So you, in your app code, you might sometimes be, okay, I want to integrate functionality with these things, but I only want to support them when it's actually available on the device. So these classes are inside jar files on the devices from those API levels, but if your code runs on older API levels, then these classes will not be available. So those classes won't exist on those devices. In this case, our methods aren't overloaded, so we have two different names. So if we call the second one by reflection, then no issue will happen, even on devices with lower API levels where the first class doesn't exist. So this is where then the minification step or the name obfuscation step comes in. Like, what if during that process certain names have been renamed and they end up being the same name? That will then introduce this problem. So this is kind of a more concrete situation where we actually encountered, where we then had to dig in, like how did this happen? Because what will end up happening in this case is that because these methods are overloaded, a reflection call will fail on certain API levels, but will succeed on API levels in a way where nothing that you're actually doing, because you're invoking a method that exists, you're invoking a method where the parameter exists. So everything that you're doing seems fine, and the error doesn't even seem related at first glance with what you're actually doing. Generally, minifiers like R8 or ProGuard will be kind of conservative in trying to avoid these issues, of course, but there are they will provide a ton of configuration options, like overload aggressively or specifying how exactly to rename methods that you can take under your control that could potentially introduce such issues. So again, like looking at source code, you won't have a clue that this is even possible in the first place because the code you wrote cannot even induce this problem. So in these kind of situations, it can be interesting to see what has actually happened to my code that is running on the device that is causing such issues. The first thing that can be interesting if you're working with minifiers is looking at the mapping file to see which renamings have actually occurred, to see if anything seems out of order there. Or in more detail, you can also look at what is inside the DEX file that has been compiled. So a nice tool for that is called JDEX, which also has a relatively straightforward UI, I would say. JDEX will basically decompile DEX code back into something that looks like Java source code to make it easier to understand what the code looks like, because you can also look, you also have different ways to look at DEX code that are a bit more closer to the actual bytecode, but JDEX will decompile it to make it a bit easier to understand. So this next section is a bit more, I guess, for fun. It's not as related to really a concrete use case. It is something that we encountered, but I also thought it was kind of fun to include as well. So let's dive into that one. It will be a bit more about the differences between what you can do in source code and what are more possibilities you have in bytecode that are not possible in source code. So to dive into that, first I will use this more textual bytecode representation of DEX code, which is called Smali. That's because DEX code is just basically a binary file that encodes bytecode, and the visual representation is called Smali. So one thing that you cannot do in source code is basically go or have overlapping catch handlers. What I mean with that is really different from, for example, using the same or duplicating the catch handler by using the same code twice, or pointing to a method that does the same thing in both catch handlers. I really mean like pointing the catch handler to the exact same instructions in the code. So that's not possible in source code, while in bytecode that is possible because it works with labels. So you can simply use the same label for two different catch handlers. So the example will involve this. Another thing you cannot do, or at least not in older versions, I think in newer Java versions they're making this possible again, but something that you cannot do is add instructions before the supercall. But if you construct additional instructions before the supercall, before the super invocation, the JVM or ART has no issues with that. It will just happily run that. So the example will also involve this. So where we can see that the supercall, which corresponds to this invoke direct of the init method of object, which is essentially invoking the constructor of object, and that corresponds to the supercall. And before that, we have two try-catch handlers. But what we have created with this bytecode right here is a situation where in the section before we have invoked the supercall, we will be referencing code. We will be referencing an object that has not been initialized yet. So an object that has been created but has not had its super constructor invoked is uninitialized, while in the catch handler after the supercall, the object has been initialized already. This is generally a situation that the DEX or Java compiler will not allow you to do. Like they will complain if you try to create bytecode that looks like this. But with the Smali tool, which can go back and forth from the textual representation for DEX bytecode, we can construct bytecode like this. So then in the section afterwards, we are simply like referencing something that, this parameter, so P0 will be the this. We are moving that into a variable, moving that into a register. Now the interesting thing that we encountered is that for some reason, this code behaves differently on certain API levels than on other API levels. I'm not exactly sure. We didn't really dig in why exactly this sometimes doesn't work or does work. I suspect it might be something to do with optimizations that are happening on the device. That's in this particular instance, because we're not doing much more with this object, only putting it inside the register. Maybe in later API levels, it gets optimized away. But in any case, this particular construction of code shouldn't even work or be generated in the first place, but it is still interesting to see that on different API levels, this behaves differently. So I think this gives another argument for testing on different API levels thoroughly. Then as the last section, let's go into the Dalvik bytecode to machine code translation a bit more. So as I mentioned before, Dalvik bytecode can be run in different ways on your device. So the first one is that it's simply interpreted. So simply the device runs, looks at text bytecodes instructions, interprets them and runs them as it's seeing them. This is, I guess, the default mode, you could call it. But it's generally also going to be the slowest mode, which is why these other two options exist. Then there is also JIT optimized code, so just-in-time compiled. This will generally trigger when you are running DEX bytecode on your device and the Android system sees like, oh, this method has been executed quite a few times. Maybe I should actually compile it so it runs a bit faster. That's typically when this will be triggered. And then there is OAT, which is kind of supposed to mean ahead of time, but it's basically ahead of time compilation of your DEX bytecode. So this is really taking the DEX bytecode before it's running, compiling it to machine code, so it will run quite fast. So let's dive into a little bit more details of how you can observe this. Here I set up a rather just simple, straightforward example of just running a compute-intensive task in a loop and then logging how much time it took. This is really like the simplest way to observe this, I think. One thing that you might not be aware of is that when you have an application installed on your device, you can sort of trigger certain compilation mode. So with interpret only, it is for a particular package, it is telling the Android system to say like, okay, I want this package to only run in interpreted mode, which is maybe a little bit confusing terminology-wise because it will still allow just-in-time compilation, but it basically means that it's not gonna ahead of time compile anything. So when we then run this method, we will see that the first run, for example, took 10 milliseconds. The other runs will take equivalent amount of time. And then if we have enabled JIT logging, we will see that at certain points, the Android system will say, okay, I added JIT for this method. It took this long. And then we start seeing that the method takes a significantly shorter amount of time. So that is the just-in-time compilation kicking in, compiling the methods in the JIT cache, and then the method runs a bit faster. We also have another possibility of triggering different compilation strategies. So if you use speed, for example, then it will basically tell the device like, okay, I want actually this package to be ahead of time compiled. And then we can, when we then run the same application with this method inside of it, we can immediately see that it runs way faster. So this is the ahead of time compilation has been triggered when we executed the previous command, and then when we run our application, the ahead of time compiled code runs instead of the DEX bytecode being interpreted or JIT compiled, and then the method immediately runs way faster. So you don't, as in when you release your app on the App Store, you don't like tell on your user devices like whether it should run in speed mode or interpret only mode. This is the Android system that decides this for you. But a way to influence that is with baseline profiles. So you can do this with generating baseline profiles, which will result in some metadata being added into your application. And then this metadata will be used by the Android system to decide whether certain things should be ahead of time compiled or not. So typically, this will be useful in determining which methods run on startup. Those can be ahead of time compiled, and then your app startup will be improved. There's more documentation on baseline profiles on the developer Android website, of course. So that brings me to sort of the last situation, which is a situation that we encountered where we basically encountered a bug in the DEX2auth. So the DEX2auth is basically the name of the thing that does the ahead of time compilation. So how we sort of got into this situation in the first place is that we were sort of seeing weird behavior with a certain test APK that we were running. Like sometimes the APK would fail, sometimes the APK wouldn't fail, but there wasn't really a clear pattern of why this was or how this happened. Until one of the people in our team saw that if we run this in interpret-only mode, it always succeeded. When we were running it with the speed mode, it always failed. So this then caused us to trigger to think like, okay, surely then this must have something to do with ahead-of-time compilation. We tracked it down a little bit further. We made the example as small as we could, and eventually it came down to something like this, where basically during the ahead-of-time compilation, so during dex to auth, it was doing an optimization, because as part of making the code faster, it will also do a bunch of optimizations, of course. And the optimization that was being triggered was incorrect. So in this case, it was like some binary or Boolean expressions being optimized across branches, but it was doing it incorrectly. So in one case, the result would be different than in the other case. And then this eventually led to a crash of the application. So this kind of gave us enough information to be like, okay, this is really a bug in the dex to auth, because initially we weren't sure whether this bug was something that we did wrong while generating dex code, or like what kind of the situation was, but this narrowed it down enough for us to see like, okay, this is really a bug that needs to be reported and fixed. So that's what we did. The thing is that, of course, so we, when we generate bytecode, we still need to take this bug into consideration. Like this wasn't exactly where the story ended for us, because even though this has been fixed on newer phones, we still support older API levels or phones that still have this bug present, so we still needed to find a way to avoid actually triggering this bug in the first place, even though the bug has already been fixed in the meantime. So as a short recap of everything that I've discussed today, so we went through all the different translation layers of source, like Kotlin and Java source, to Java bytecode, to Dalvik bytecode, eventually to machine code. So Kotlin and Java sources are compiled to class files. They run in the JVM. You can find these in the build folder. Java bytecode is then compiled into dex code. Dex code runs on the Android Runtime. You can also find the dex code inside the build folder of your Android project. The dex to machine code has specific patterns when it's triggered or not. It doesn't always happen. You can specify while debugging ahead of time compilation to potentially find if there's or measure performance improvements or see if there's any bugs related to that. The ahead of time compiled code is not going to be in your project because that only happens while your phone is running. But you can find them on the device if you want to. And at the bottom here are maybe a few examples of when you should think about something is related to this specific part of the translation. This is of course not really an exhaustive list or anything like that because there are so many different things that can go wrong. But these are just a few examples of when you need to think like, okay, maybe something is wrong in this case. So if you have a compilation error, like we saw in the beginning where we were calling Kotlin from Java, something went wrong, maybe there is a misunderstanding in exactly how Kotlin code is compiled and you're not using it the way that maybe it's intended to. If there is a difference in unit tests versus other kinds of tests, maybe it could be related to a difference on running on the JVM and the Android Runtime. If there are certain classes or methods or resources not found, it could maybe be related to the dex bytecode translation, either with the 8 itself, but usually it's going to be another element that you've enabled, like R8 or ProGuard, that is maybe doing things too optimistically and removing things that you don't want to be removed. And then for machine code, it's really going to be sort of patterns that only happen while your app is running, and probably only in some situations or not in other situations. So maybe only after certain code has been running for a long time. So maybe it is JIT related, or only when ahead of time compiled. So these are kind of examples of when looking or investigating into these translations could be relevant. So that is the end of the presentation. Since we have a few minutes left, I think I can take a few questions. So please, if you do have questions, you can use one of the microphones. We also have a booth in the sponsors area next to the balancing board. So if you want to come check us out at the booth, you can also ask us questions there. Thank you.